So Gen3D's SULA software accelerates the designs of additively manufactured components, specifically looking at fluid flow components. So there's a number of bottlenecks in the design process with traditional software, and what we try to do is solve the problems that those bottlenecks are providing and just reduce the number of design iterations that are required, improve the performance of the designs and the components themselves, and try and give feedback to the users of how manufacturable or printable a component is.
When we first set up the company back in 2018, we were focused on generative design, but we soon realized that actually there's a big market gap for fluid flow components, particularly where there's sort of tortuous paths you have to flow for your fluids. So we realized this quite early on, and we also recognized that there was no design tools out there to do this adequately. So therefore we developed the SOLIS flow package to allow us to develop these really complex flow paths, specifically so that it can be additively manufactured for a variety of disciplines, from aerospace, automotive, oil and gas, wherever really. Wherever there's an aspect of taking flow from A to B in whatever pattern you choose that to be, this is where we can really add value. INFLUUNT is about developing new design algorithms specifically for our software, SOLIS Flow. So the biggest problem with additive manufacturing is that on the face of it, it seems quite straightforward to do. But in terms of actually designing for the process, it's really, really complicated, and the design tools that currently exist are inadequate. So we developed this project, INFLUUNT, to try to develop new design features which we could then put into our software to accelerate how people use additive manufacturing in a progressive way.
So without NATEP support, we would only really be able to do quite small development projects. We're a startup, and being able to develop really, really large bits of technology takes a lot of investment and a lot of time. And because of that, the NATEP support really allowed us to do something a lot bigger that we were never able to do before.
So some of the advantages of additive manufacturing include being able to place material where you want. So if we consider these two hydraulic manifolds here, the aim of these objects is to basically take a fluid into these objects and transfer it into different locations to be able to, say, actuate a wing of a plane or something along those lines. Now, as you can see, the way this manifold is built is to start with a big block of metal and then to drill holes into various sides of this object. Now, one of the downsides of that is that we end up with lots of 90-degree corners. And fluids in general don't like going across sharp corners. And when they're made to do that, it means we need to input more energy into the system to get the fluid to move around these corners. As you can see in different areas of this manifold that we've 3D printed, the fluid channels are much smoother in their direction. And this means that we can put less energy into the system to get the fluid to move around the manifold object. So something like this weighs around 85% less than an object like this. So if we think about this in terms of its end-use location, say for example in a plane, we can use much less fuel as we fly these objects because we're just carrying much less mass in the plane. Gen3D engaged with Domin partly as a designer and then partly as a software provider. So Domin design components like this a lot of the time. They're looking to apply the advantages of additive manufacturing where possible. And Gen3D are looking to find end users for our software where we can help people design fluid flow components like this.
So additive manufacturing has huge gains to be made in aerospace engineering because it's all about lightweighting. If you can lightweight components, you can save fuel, you can reduce your buy-to-fly ratio. Basically means you can make the process more cost effective. So what we can do with our software is significant lightweighting. So this is why we targeted aerospace. So as project manager, we chose to work with the University of Bath because of their high-level research capability. So we're a great company in terms of developing software, but in terms of research and expanding that so we can create algorithms that are right first time and develop software that is reliable, it's in our best interest, we felt, to have the university on board so we get that sort of high-level R&D, but also the development as well from the company, and marrying the two together gives us this win-win situation.
In hydraulic components, additive manufacturing is a game changer. Not only does it allow us to reduce weight and to reduce part count, but most importantly, it gives us design freedoms that we've never had before. So the NATEP project funding allowed us to investigate the pressure flow characteristics through complex 3D flow paths in the AM components. So these flow galleries are not possible to manufacture using traditional methods. So we need to investigate this new type of flow path. And it's important to minimize the pressure drop within the flow path in order to make the hydraulic components more efficient. Well, the university is all about trying to create new knowledge and understanding, so it allows us to do that, but we also want to publish that so the community at large can benefit from that new understanding. We also want to work with end users, so a collaborative project such as this, working with Gen 3D, allows the industry to actually make use of our research, and the impact is important for the university as well.